Hey, so here I find myself doing a little bit of OpenSees coding. Maybe I'll devote an hour or so to this. I'm working on a plasticity model, which is inspired in the hardening soil model by Plaxis. And I'm doing this in my new framework of plasticity, ASD Plastic, which is a collaboration with the good guys at ASDEA. So right now I'm going to be doing some testing. Um, I'm here in my OpenSees folder, and I'm working off a clean checkout of my personal branch, which has where I'm doing my development. So I'm working a lot in this branch, and then when I want to push stuff into OpenSees, I'll branch off the master, merge the changes, and do a clean Git, a single large Git pull request or push request into the main OpenSees repo so that Frank and Michael can take a look. So anyway, I'm here and I'm with a clean build of OpenSees. So you can see the make system is compiling OpenSees and OpenSees PY. And in this lib folder, I have the shared library for OpenSees PY, and I have a link to the OpenSees.so because on Linux, if I want to use the library, this is the way I've figured out. So figured out how to do it. So let's open up a new terminal over here, and I'm gonna navigate into my Dropbox folder, the projects folder, ASD plastic material examples folder, and in here I'm gonna be working on this test over here, the stiff soil, and let's take a look at that real quick. Let me switch like this. And I'm going to open VI into this folder. Let's bring up the font size so you can take a look at what's going on. And over here, I'm going to open stiff soil shear.py. So this is what I'm working on. Let's remove that sidebar. So this is what I mean. This is how I'm importing OpenSees PY lately. So I am appending to the system path basically the path to this folder over here, to the folder that is in this other screen. That's going there, so it can find, and if I do import OpenSees, it's gonna expect the path to have an OpenSees.so, like I have here. So that's how it knows how to import everything. Yes, 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 indeed. So this is where I want to be working. Over here, I'd like to have this folder open, and let's take a look at the component that I'm going to be checking right now. So it's going to be the stiffening soil elasticity.h. Let's bring up that font size, and then if I want to do changes to the source, I'll use this terminal over here to take a look. And then if I'm working on Python, I'll have a similar setup on this other side. Anyway, I'm working in this little model over here. This is the elasticity component of the soil model. And if I execute this script over here, let's take a look. So I want to do test stiff soil shear.py. I'm getting a whole bunch of nada numbers. Okay, so what is this script doing? It's defining, it has a bunch of parameters for the stiffening soil model, and I'm defining from the ASD plastic material, which will do an official introduction with the good people at ASDEA soon. This is a joint collaboration with them, so I had to appreciate their willingness to basically finance the development of this model. It's a whole family of plasticity models. I'm really proud of this work. Anyway, so here I'm working on the stiffening soil yield function. I'm selecting stiffening soil, plastic flow direction, and elasticity. And here's a bunch of parameters. I won't get into that, but I want to show you what the script is doing right now. At the first step, I'm getting the tangent stiffness. And then I'm going to be doing a load in the along the hydrostatic axis first. So we want to reach a target strain, which is given by the sigma 3 target. So basically up here, sigma 3 target, where is that? Where did this guy put it? Sigma 3 over here. So 100 kilopascals for the sigma 3 target. So I'm going to try to aim in the deviatoric direction, so basically isotropic in all the epsilon directions, until I get to the target strain that will produce the target sigma. And what I'm seeing now, I have this little constitutive tester function that we can take a look. Let's undo that, bring up the constitutive tools, and you'll see here this little tester is just using OpenSees, and it's using the ND test option in OpenSees, which I programmed, but it's not documented. I should document that and push into the main documentation. And over here, so I'm calling that tester so that it basically goes along a given strain path, and I get the stresses out. It's very simple. And I want to see what the mean stress is at the end. That's what it's doing, and I'm getting, these are all the steps, so I'm taking 20 steps in the time series, and these are the outputs from each step, and I'm seeing lambda is minus not a number, and mu is minus not a number, and that's coming from the OpenSees source, which is over here. Over here, I have these cout statements because I want to take a look at what's being input into the model. So let's take a look. This lambda and mu are constructed from these values over here, nu and the epsilon ur, and that's coming in turn from here. So let's just take a look at all this stuff. I'm gonna yank this line and paste it a bunch of times, and I'm gonna take a look at all these components. So for example, here, eur ref, and I'm gonna replace this one by, I still have my chops, eur ref, and let's take a look at eur, and again here eur, eur, like this, eur, sorry, that's boring. And let's take a look at what's here in nu, which should be our Poisson ratio. Nu. There should be a way, Vim. I'm learning how to use new Vim. I'm slow because I don't get to code a lot. But there should be a way to modify these two things in some fashion. So, for example, no, let's just focus on what I'm doing. Let's focus. Let's get mu. No, mu, I already have it. Ur ref, and let's take a look at that denominator. That looks suspicious. That would if that's zero, it would produce another number. So we're gonna investigate that, the denominator, and I save, and now I compile. And let's take a look at what's going on. This is a heavily templated library, so this takes a bit to compile, but I think I'm not in release mode, so it's not going to be that bad. So I want to go to this terminal and just run the test again and see what happens, see what is happening. So the uref is 90, denominator 62, eur is minus not a number, and that means my problem is elsewhere, right? Let's take a look at eur. Unload, reload. It's coming from this max expression, which is eur, and eur ref. Let's take a look. Eur ref is 90. So eur is coming from this one over here. Let's break this down, shall we? So eur is made out of uref, which we already have the denominator. Let's just delete that line, and I'm gonna paste it up here and paste it again so I can have the I'm so clumsy. Numerator, and over here the numerator, like this. I want the numerator, EUR, and M. Let's bring out M. So paste, no. Let's do a yank and a paste, and CIW M, and over here CIW M again. Save, compile, compile. And the compilation process, yeah, it's pretty fast. It's fast because I am just working on these components too. Like, for example, for this new plasticity class, there's this all model parameter types. Where is this? ASD material definitions. This guy over here. So this C++ file has all the models I'm trying to instantiate right now. And because I'm working just on the stiffening soil, I just have the shear component and the cap component. But I could have all the models here, like the Moore Coulomb and the von Mises and the Drucker-Prager and the different evolution laws, and it gets crazy and it's templated and it's going to take a lot of time to compile, but it's going to be efficient. That's what we get. So users are not typically compiling the code, so they don't care about this. They just care about code that works. So let's test this out. This is just going to print out the variables I'm interested in. So let's go all the way to the top, around here, and we can see that it starts off with reasonable values for everything. M is 0.55, but then the numerator becomes minus not a number. And that, my friends, is weird. It is indeed weird. Why is this happening? Because we have nice values here. We have nice values here, and let's do something else. Let's try to matrix set 0. So that first step is kind of crucial, actually. Let's try to constitutive tester. Let's try just to do one step. Let's do one step. How do I get that to happen? So I'll just index here. I'll index the first step like this. Does that just give me, oh, what did I do? Did I accidentally close that window? I think I did. No matter. Here we go. I need to, no. Save. Go. And no. Epsilon function preload. Okay, so this is T. And I guess epsilon function preload of T. This gets called at each time step, doesn't it? It's just a function of T. Yes. So this constitutive tester should just be doing one step. Should just be doing one step. Should I have some music on? Does it make sense to have music? It might. If I'm doing something like this. Constitutive tester after consolidation. It should be doing. How about let's do it like this. Let's erase here. And here, that's T. Let's just replace what T is. Let's just get the first component. What is this doing? I just needed to take one step. Step 1 of 20. Epsilon function. This is just a function. Why is it not doing what I think it should be doing? Is it because went like this? Let's see what's in there. T is just one step. Okay, let's take 2 steps. There we go. One of two, one step. And then the stress values that I get is not a number. Let's investigate that. Actually, let's take 3 steps. That should be enough. That should be enough. Okay, 2 steps. So then in the next step, I get the numerator none. But the first indication that I have something weird going on is the fact that after this step, the stress values. Okay, so if I take 1 step, I can see the stress values are not a number. Let's investigate that. So the first thing I'm going to investigate is actually the elasticity. Now, these are just a collection of mu's and lambdas over here. So let's go here and just see out, let's call the EE matrix like this and the EE matrix. Let's see if this will compile. Oops. I still have my old muscle memory that makes me do stuff that I don't want to. While that compiles, check that everything is fine in the rest of the world. Okay, there we go. So now let's compile. Sorry, let's run that. So here's the matrix. It looks fine. Strain values are all negative, and that looks fine. And then I get stress values. Okay, so there is some other component that is giving me trouble over here. This matrix looks fine. I want to take a look at whether or not the integration is going well. So I'm going to go into the gut of the ASD plastic material, which is this huge, very templated function. And I'm supposed to be using the backward Euler integrator. So I'm just going to check real quick if backward Euler is what is being used. Let's navigate to this part of the code. Backward Euler. Let's just really quick add some code over here. And let's say cout. I just want to make sure that it's getting called like this. Compile. And then just making sure that I'm calling the correct integration method. Otherwise, I'll specify it manually. BE call. Here we go. Okay, so from there, let's print out the yield function values at the start and at the end. So let's do that. I am going to yank this line and paste it over here. Paste, new line without a paste though. So let's go here. So this should be CI like this, and YF val start. Let's go equals and YF val start. I'm actually regretting. Let's do like this. paste, paste, and delete, delete, and delete. And I'm gonna go here and just old school style go end, and then old school style go end. Maybe there's easier ways to do this, but this is the way I'm using right now. And I want to take a look here what's going on with the yield functions. So, not a number. So the problem is actually the yield function. Okay, progress. So stiffening soil, let's go stiff YF. That should bring the fuzzy search into where I want it to be. And yep, there's a whole bunch of stuff here that can go wrong. So what I'm gonna do is, like before, I know this is not a number. So I think I'm just gonna print out everything. Let's just make sure everything is working just fine. So let's Yankee some of this stuff over here. And first paste, 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 paste. Okay, so this is where I'd love to be in Sublime and just grab all these stuff and do a quick paste of everything. We are not in Sublime land now. This is not how it is. I wonder if there's a way to do this. Would you care to go on a tangent with me on this regard? Like, I know there's the visual block mode, which might do something close to what I want to do. Like if I go CV, no, I'm messing up stuff. Control CV, that's visual block, and it allows me to select blocks. That's close to what I want. But what I really want is a multi-cursor. Multi-cursor. I need to get a Vim brain. Anyway, let's not waste time on that. So this should be phi, forward D, CIW, phi. Okay, CIW should be C, forward D, CIW, C. Forward D, D, forward D, forward, CIW, and I want E50 ref. Forward D, well, forward D, CIW, E50 ref. That's pretty fast. Forward D, forward D, forward CIW, and now I want PREF, forward D, oops, forward D, CIW and PREF, escape, forward D, FF, and CIW, and I want RF, escape, forward D, CIW, RF, forward D, forward, forward, and then EUR ref, so CIW, EUR ref, escape, forward D, CIW, EUR ref. Okay, that felt good, kinda, not too slow. But in Sublime, I could have done that like in 2 seconds. I need to figure out how to do that. I need to figure out how to do that. Anyway, here we go to our test, and over here, E50 ref is 0. That is suspicious. E50 ref is coming from up here. E50 ref should be 30,000. Let's take a look at this stuff. Is it correct? And I have M. Yeah, that doesn't look okay. E50 ref is 0. P ref is 100. Is that okay? Yes, it's okay. EUR ref is 90, but E50 ref is 30,000, and RF is 0.9. And the phi and the psi angles are phi and I'm not printing those two out, so for now we'll just ignore them. But this E50 ref should be 30,000. Why is that not the case? Go back to the source, E50 ref, SS E50 ref. That is where we're getting our stuff from, right? Is it the case that is overridden, maybe? By someone? Somewhere? E50 ref. E50 ref is this value over here, and it's being set to 0. Let's take a look at what the material thinks it's doing. Yeah, this is wrong. E50 is 0. E50 ref is not 0. Okay, so that is a lead. So E50 ref, let's actually get E50 out. E50 though is supposed to be something with E50 ref. Huh. Okay, so the parameter is called E50 ref, SS underscore E50 ref. And SS underscore E50 ref, that's where it's going. Why am I not getting the correct parameters? This should be one of the parameters specified down here. So that's looking fine. Let's take a look at ASD parameter types. Should be E50 ref. It's because this name over here should have ref over there. Right, and recompile. I messed up that one. Here we go. I messed up that one. So now that OpenSees has been recompiled, I'll try it again. E50 ref is now 30,000. Okay, so that is good. That is good. However, we're still getting some weird stuff. So let's take a look. The first step, let me take a look at the yield function values. YF start is 0, YF end is not a number. So we should take a look at why that second yield function value is not a number. So actually over here, let's just put some space here. I like this because it's easier to find in the output. And save that. And ASD plastic materials. So the start and the end, the trial stress, I may want to take a look at what the trial stress is. Let's have that one. Okay, so yank this, paste it, and let's over here CIW trial stress like this, forward Y, and then CIW and trial stress. Save and recompile OpenSees. Hi people, I see there are some concurrent viewers. So if you have any questions, I'd be happy to answer them. Anyway, I just compiled OpenSees, going back to the test and taking a look here. I want to take a look. So the yield function at the start is 0. The yield function at the end is minus not a number. And the trial stress, it's going in the direction that I want. It's going in along the deviatory plane. There's no deviatory component to this trial stress. And that yield function value at the end should be, of course, a negative value. So let's take a look at why. I should go in here. What did I do? I didn't save it. So what else can we do? Why is it that it's not a number? So we convert to geotech stress and get the deviator and get the principal stresses. Let's just take a quick look at all this stuff. Yank this line, paste, 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 new line. And I'm going to take a look here at the deviator, at the principal components. This might be part of the issue because I'm going in the deviatory component, all of these are going to be the same. CIW sigma 1, CIW sigma 1, forward E, forward E, forward, CIW sigma 2, forward E, I need to press escape, forward E, no, forward E, CIW sigma 2, my hands, CIW sigma 2, like this, and escape, forward E, forward, CIW, no, what did I do? Oh Lord. No, it got rid of that. What did I do? So I want to redo. That was control R. R? No, that's just a delete. Here, CAW. I'm so clumsy with this, I'm sorry. Forward E, forward E. You need to be accurate with your fingers. I'm not, sigma 3. But it feels great. I like this. And let's take a look at the stress deviator. CAW, no, CAW, Q, escape, forward E, CAW, Q. There we go. Recompile. Recompile OpenSees. And we'll go back to our test and run again. In this window. Yeah, the sigmas are what you expect. And the deviator is giving me a none. Of course, because the deviator is 0. So I need a guard there. Get principal stresses, the stress deviator Q. So that function's all wrong. The function that gets the stress deviator. This is defined in, I think, is it in type defs? Well, let's take a look. Stress deviator Q. V11, V11, V22, V22, V33, V33, minus V11, V22, V22, V33. I wonder if this stress deviator get J2. How about if I do the get J2 function, which I know that I use it elsewhere, and then I do this by hand. Let's do that quick check because these two expressions are not looking the same. Or maybe I should replace here void vector, get the deviator, this deviator J2, get J2. So maybe instead of that, I'll just let's delete these lines and just call double J2. This get J2. Yep, that way we're reusing code. I'm not sure if that previous implementation was correct. So we're now rebuilding. Hey, dear concurrent viewer, what's up? And let's see what happens. That worked. So I was using the wrong J2 function, but I fixed that. So I'm getting a Q, which is essentially 0. And my yield function, let's see where that stuff is. Yield function start is 0, yield function end is 0, essentially. A slightly positive value, very slightly positive, but it looks like stuff is working. We are 35 minutes into this debugging session. So what I'll do now is I'll go here and I'll ask it to do more steps. And let's see where this takes us. So instead of this, let's just erase that line, save, go to the terminal, and this looks wrong. And the reason that's wrong, my friends, is because when I do this approximation, it assumes that I can reach the sigma 3 target using the E unload reload modulus directly. So this value up here. But this soil actually stiffens. So if I keep going, the soil will get, that modulus will get harder and harder. And if I use the initial prediction for that, I'm not going to get the right value here. So actually, for this test to work, I would need to update the epsilon function values so that I can adapt basically to the value that I need. Now, what's a good way of achieving that within this particular source code? What's a good way of doing that? I can't use the predictor that I have here, the preload, or I could update that somehow. What's a good idea here? Well, let's be lazy. This is about 600. What happens if I divide that sigma 3 target by, where I keep messing up. So here, I'm going to divide by 600. Simply that. Save, go down, and I'm at 0.25 kilopascals. So that was too much. So let's work with this number. What if I go for 500, for example? 0.30. What if I go for like this? I'm dividing by such a big number. No, this should be something like a factor of 6, actually. That was stupid. So save, go down, and retry again. That brings me to 29. So that is a bit too much. Let's go here and insert mode. What if I divide by 3? This is just 87. I need a little bit higher of a number, 2.5 maybe. Let's get rid of that. 119. And 28. That's pretty close. 98. Do I need higher or lower? I'm not thinking anymore. 75. Oops. IP address show. Because I need to show my IP address information in a live stream. That's important, right? Oh, look, that's that looks like atmospheric pressure, actually. Atmospheric pressure. It's 1 in kilopascals. kPa. It should be 101.325. That's my brain does that. I'm sorry, but this looks like atmospheric pressure. Anyway, 39 minutes into the stream. So now at the end, let's print the stress values. The stress, we're where we're supposed to be before we do the deviatoric part. So I'm happy. we found some bugs, and we can keep going. So let's delete that X. And now what's going to happen is I'm going to press in an axial direction. So take a look at this. I'm going to take the values at the strain end. So this one, right? And gonna add an additional strain to this. So it's gonna be going in the deviatoric direction. By that I mean just in the axial direction. So I'm just adding an axial component, and that's going to be to a maximum value of minus 0.1 axial. And let's see what this does. This is going to nan out, I am pretty sure, but it's going to be some progress. Yep. But look, it did some stuff. It did some stuff. And what's complaining here is actually Python. But it's complaining that arrays must not contain infs or nans. So I suspect, yeah, it all went bonkers at some point. So I need to keep debugging. The EE matrix is going. So let's do the same idea. Let's do the same idea. And what I'm gonna do here, before the test, where's the test? Ah, here's the test. Plastic strain values. Let's just get here and add some lines, and I'm gonna add a little exit 0 so that the script doesn't continue beyond this point. And the T, I'm gonna do the same trick as before. So I'm just gonna do a few steps. So let's go for 2 steps, just as before. But now we're loading the deviatoric direction. So we're going out of the hydrostatic plane into infinity, into not a number, basically. But this is not working. This is, oh, did I put it after the consolidation phase again? So let's grab this, D, after consolidation, and I actually want it over here, P. And take a look. It's trying to do plastic integration and it's getting some error. So this is good. 4 iterations and I have some error. So it's going fine until it doesn't go fine. So maybe this epsilon axial, let's see how far we can go. Let's see how far we can go. How about if I go all the way to 50? I start getting not a number. I start getting not a number. So maybe I need to figure out if I get a not a number, I need to tell the constitutive tester to stop. I'll do that. I will do that. If for example, sigma contains a not a number, I'm just going to just return. Let me take a quick look on how to get this done. Yep. So I'm going to break out of this for loop in Python if I find a not a number, basically. So let's go if how do I do this in Python? So this sigma is going to be, do I have a numpy dot is none? And I don't know how to do Greek in Vim. There's probably a plugin for that, but it does not matter. If is none sigma, then we're going to break out of that loop. Let's see what this does. Is none. Okay, so that is this should be the component wise, and and I should go like np.any. If any of these numbers is a none, is a not a number, then there we go. And let's add a little bit of print. And here let's do none found, exit, sad face. There we go. That makes sense. That makes a lot of sense. What's up, chat? I'll be ending the stream shortly, but I just want to see where that none is coming from. So the none is found, and I wonder if I let it go after that none is found. So let's oh, I can't remember that GC. Let's comment those out. Should be visual mode GC. Again, I'm doing GX. Damn it. Visual mode up GC. Comment. There we go. Victory. Now, what happens if I run this? Does it should run all the way. None found, exit. Okay, so what if I comment that line out and then just let it run and give me some plots? It's not gonna give me some plots. Okay, but after this, we can take a look at what was happening that led to that not a number. Not a number. Sorry, brief interruption. Let me close my door. Here we go. So where's that not a number coming from? Do we see not a number over here? What's going on? What is going on? Here's a hint. Yield function value start is minus that, and the end is not a number. So we can see this value. This is basically a deviatoric. So you can see the sigma x is pretty much 0. I mean, pretty much a negative number, but then we're getting 0. So maybe we're getting, yes. This is okay, so this is going towards the tip of the cone, of the Moore-Coulomb cone for this constitutive model. And eventually this is going to fail because the yield function it's going to depend on this Q value, and Q is a decent number. Q is looking fine, but I'm pretty sure what's going on here is that we're losing confinement on the other directions. And the problem with that is eventually we go out of the cone and it doesn't know how to return to it. And this is because of our flow rule. So maybe I should try this out with a different flow rule to start. But yeah, I'm gonna go off stream to do this stuff. I can see there's some concurrent viewers. I appreciate if you guys are taking a look at what's going on. But I think 50 minutes of stream is more than enough. Let's see if you like this, give it a like, maybe leave a comment if you like this kind of content, if you want to know where this goes. I do some coding, but I keep it off stream. Just today I wanted to keep it on stream. So anyway, see you guys next time. Let me know if you like this. I can do some more of my own personal